Alright, so welcome back to particle physics and a standard model. This is lecture 57 and last time we finished up on our learning of the sequence of the arrival of the Z boson into our world, right, into our knowledge at least, right. So what did we do? We saw that it was indeed the forward backward asymmetry that was a key observable historically, the forward backward asymmetry being, you count all the events in the forward direction, count all the events in the backward direction, take the difference and normalize by the total number of events, right, which remember it turned out to be 0 in QED because parity was conserved in QED, but no business for it to be 0 in the weak interactions generally, especially those mediated by the Z boson, W boson and so on, right. And indeed as a function of the center of mass energy of whatever particles that you are crashing in the plot that I am showing here in as the particles are the positron and electron, the final states being BB bar. If you plot this as a plot the forward backward asymmetry as a function of the center of mass energy, you do indeed find that as you go to higher energies you get a non-zero forward backward asymmetry, right, and it goes to a negative value because it turns out that is how interference between the amplitudes mediated by the photon and the Z boson go. Okay, it is an intricate interference, but then as you go to higher center of mass energies higher than the Z boson mass, it again flattens out because the interference term becomes negligible and it's the mz square term starts dominating. So it is as though you have added another gauge boson, a non-interfering gauge boson to the theory, okay, but this time with parity violated. So seeing these hints is how people knew that the Z boson was really around the corner, and that immediately led to Nobel Prize, the Nobel Prize for the theorists Glashow, Weinberg and Salam, because it really vindicated the standard Elter-Weak theory, which already started being called the standard model back then. Okay, and of course we talked a little bit about the history. People saw the forward backward asymmetry and then Carlo Rubbia built a collider at 100 GeV center of mass energy and actually discovered the Z boson, and similarly Simon van der Meer discovered the W boson, okay, and they also got the Nobel Prize in 1984. Okay, excellent. So that nicely ties up all our discussions about the electroweak sector. Okay, we started all this by talking about parity violation in terms of just the discrete symmetry, then we saw parity was maximally violated in the weak sector, then we understood what we meant by the weak sector and the weak interactions and the Elter-Weak force, right, and how it is broken by the Higgs mechanism and what do you get after the breaking, all the wonderful consequences in the flavor sector and in the gauge boson sector, and how we finally discovered, how we actually discovered them in colliders. Okay. So we have turned the page on the Elter-Weak sector, which is really one of the great triumphs of physics if not science. Okay. So we are going to come to our very final sub module of the course, which is another super interesting, super important phenomenon, experiment, however you want to call it, that also helped us understand not the electroweak sector now, but the strong sector itself, okay, and that is called deep inelastic scattering. Okay, we will inspect all these words now. Okay. The idea here is simply that you want to hit protons and neutrons with something in order to break them up. Okay, I will just write this very colloquially, hit nucleons, that is protons and neutrons, and break them up and study their constituents, okay, and that way get to know what is inside the neutron and the proton. What are they? Quarks and gluons, right. How do we know if all this wonderful quark model, okay, and the SU3 and confinement and all of these, how do we know if that is really true or not? We need to do an experiment, right, that is exactly what this is. Okay. So let us start at the beginning. Let us see how we can actually resolve the structure of a proton. Okay. So resolving proton structure. alright. So, suppose I had a proton which I am drawing this way, and I have a probe, okay, some electron or some photon or whatever, okay, and the probe is low energy, so that you know the wavelength is like this, okay. Then this is a scenario for which I can write the cross section as, you know, it is like, so the differential cross section, if you will, is, you know, something like this, 4 pi alpha squared, where alpha is the fine structure constant, over q squared, okay, and I am going to say into 1, you will see why in a second, okay. So, what is q squared? That is nothing but the, you know, q is nothing but the momentum transfer. Okay. So, what I have drawn here is not really the wavelength of the particle itself, okay. It is has this already covered one wavelength, I think so, yes. So, this is basically okay, I have not covered one entire wavelength, but just imagine I have, okay. This is basically the de Broglie wavelength of scattering, okay. That is, this is nothing but 1 over q. There is probably a factor of 2 pi or something somewhere, that is why I am putting a tilde here, okay. But what is the point of this? It means if the momentum transfer is small, okay, that means whatever the constituents of the proton are, then the de Broglie wavelength of the scattering process, right, the de Broglie wavelength that is being used as a of whatever the probe is, right, which is inverse of the scattering momentum transfer, is larger than the size itself, and so it does not really see what are the constituents here, it does not really know about the constituents. You see what I am saying? The wavelength is larger than the size of the proton itself, it sees the proton as a point particle, that is the whole story here, okay. So, this is a case where this is where I would just call it coherent elastic scattering. Why elastic? Since it as a point particle, does not do anything to it, the kinetic energy is conserved, okay. Good. Now, suppose I put in more momentum transfer, okay, so that the wavelength is smaller, the de Broglie wavelength of scattering is smaller. I am using all these words very carefully, okay. This is not the Compton wavelength, this is not the de Broglie wavelength of the incoming projectile, it is the de Broglie wavelength of scattering, it is 1 over q, it is a very specific quantity, okay. Suppose that is the wavelength of the probe, and then I keep the proton size the same. So, you can see now that this wavelength, right, now I have drawn a full wavelength, this is like comparable to the proton size, right. That means I can kind of sort of see what is inside the proton, it is no longer just a solid blob like here, okay. There is something, it seems to know something about what is inside the proton, okay. In other words, I will start having a loss of coherence. What is coherence? When you scatter, the amplitude for scattering on all the constituents, in this case of course we know it is the quarks, the amplitude for scattering is all in the same, if it is all in the same phase we call it coherent, right. But now we are going to lose the coherence, clearly they are all not going to be in the same phase, right, because the wavelength is now comparable to the size of the proton itself. So, the nucleons inside will not see the probe at the same phase being PHASE, right, okay. So, now the way you would write the cross section is you still start by writing alpha squared q squared. So, here I am thinking of basically a photon as the probe, Okay, that is why I am writing alpha square, the fine structure constant of electromagnetism. But to capture that loss of coherence, I am going to multiply it with not 1 now, but a function that is smaller than 1, and that function is usually parameterized this way, f square of q square over lambda qcd squared, okay, where this f is basically, it is called the form factor, okay, and the key is it is less than 1. And the way it goes is, if I increase q, then the smaller the wavelength is, correct, and the more the loss of coherence. So, f square will decrease basically. Basically this means you will lose out on your cross section, your cross section is suppressed with increasing q, momentum transfer. Okay. Finally, in the extreme case, suppose I have a really energetic probe, okay, that is when I can actually start resolving the inner structure of the proton. What I have drawn here are what are known as the valence quarks. We know that proton is made of UUD, for instance, right. So, we start seeing all that, okay. This is what I would call deep scattering, sorry. So, okay, deep, because I am now scattering on the constituents themselves. Okay. Of course, we know what the constituents are called. You must have heard this word before, if not you hear it here. They are the partons, because they are part of the nucleons, right. So, Richard Feynman came up with this name. Marie Gell-Mann hated it, but we still use it. Okay. So, d sigma, in this case it is schematically like this, we will see the exact expression soon. It is like this, okay. What are the Q's here? They are the charges basically, okay. These are the electric charges of the constituents, these of the quarks basically. So, there is an alpha squared, but then the actual QED coupling is Q times E, right. So, that is what is reflected here, okay. So, this is what we are going to see, this is a schematic of what we are really going to see in more detailed glory, okay. Good. Now, let us draw a more serious diagram as opposed to a cartoon. I am going to draw a Feynman diagram, okay. This is not strictly speaking a Feynman really a Feynman diagram, but it is mostly a Feynman diagram, but it represents deep inelastic scattering really well, okay. So, the idea is that I want to scatter some electron, okay, on a proton. So, I am going to draw the proton as a thick arrow to show that it is a composite particle. So, I am scattering an electron on a proton, which I am representing with this blob also, okay. So, let us call this momentum PE1, let us call this momentum PE2, this momentum is P1, but I am going to draw something interesting now. The final state is not a proton, the final state is a broken up entity, okay. This is why it is not really a Feynman diagram. This is, the left half is all a Feynman diagram, most of this is a Feynman diagram, but the purple part that I drew, that does not belong in a Feynman diagram. It is just a depiction to show that when this happens the proton has broken up, okay. So, and I can associate some 4 momentum with this whole thing. So, I will just call it some W. Okay, it is just the 4 momentum, the total invariant 4 momentum or the total invariant mass basically, but the total 4 momentum of the final state, same thing. Okay. So, what can this exchange particle be in this channel, in this mediator basically T channel? So, that is either a photon, it could be a photon obviously, right, electron is charged, proton is charged. It could also be a Z boson. Remember, every time you had a photon you could always think of a Z boson also doing the same job, right. So, at high energies you will feel the effects of the Z boson, at lower energies you will see the effects of the photon. Okay. Now you can tell me what is the momentum transfer in this process. Let us say in terms of PE1 and PE2, that is just PE1 minus PE2, correct. Now we know that the proton is, what is the mass of the proton? About a GeV, right. So, let me just write that mass of the proton is around a GeV. So, that also tells you that the size of the proton is around inverse GeV, right, inverse lambda QCD scale, however you want to say it. Okay. So, that means if I if my momentum transfer is larger than a GeV, or said differently, if the momentum transfer is squared, okay, we will see why we are squaring it soon. Okay, it is that turns out to be a more useful quantity. But the idea is, if the momentum transfer is greater than a GeV, then according to the cartoon that we have just been looking at, right, like this heuristic picture, that is exactly when I start probing the interior of the proton, right. So, this is the regime that corresponds to deep scattering. Okay. Now, if the proton had not broken up, right, then I think it is worth writing down. Okay. If proton had not broken up, unbroken, then what would W squared be? That is just the mass of the proton squared, right. Of course, that is what it is. The 4 momentum squared is the invariant mass squared, correct. But we have broken up the proton. Okay. So, that means what we have is actually W squared greater than MP squared. Okay. You can work this out. If you break up a particle into a million, or 2 or 3 different pieces, make sure that 4 momentum is conserved in that process, and then actually add up the 4 momenta, or add up get the energies and the momenta and all that, you will find that 4 momentum is conserved, but you will explicitly not conserve kinetic energy, right, and you will find that the W squared that you get at the end of the day is greater than MP squared. Okay. So, I am just explaining why it is greater and not lesser. Okay. Because of this, we are in the regime of inelastic scattering. Okay. Again, that is because the kinetic energy is not conserved in the process. Total energy is, but kinetic energy is not. Okay. So, I am just writing this a little explicitly. E1 plus EP1 will be E2 plus, what is I? All these constituents, the broken up constituents, right. So, this is true and this is also true. P1 equals PE2 plus sigma Pi. Okay. So, now you can go and do this yourself, use this and it is very trivial to see actually why the kinetic energy in particular is not conserved. Okay. Just take the total energy, remove the mass energy from this, that is your kinetic energy. Okay. And you will see of course that this is an inelastic process. Okay. Okay. Now, let us draw one more picture, but now I am going to draw it in real space. So, I am going to switch colors, alright. What is actually happening is, so this is the proton and I will just draw the constituents, these are the constituents, okay, just a cartoon, and I have an electron. I am going to choose my coordinate system such that this is horizontal, this could be either an electron or a positron, okay, and it hits some constituent and flies off, alright, flies off at some scattering angle in the lab given by some theta, okay, and this is again the same, the electron or positron still remains intact, okay. I have not drawn the final state proton, it basically breaks up. So, what can you measure now actually in this process? Now that I have drawn this diagram, in the final state what are some things that you can measure? Obviously, I start with the proton, right. The proton could be in a beam or it could be just sitting around, does not matter, and I know the electron beam, I can prepare the electron beam or positron beam in the initial state, right. I can now put some detector over here, right, and measure two quantities. Can you think of some quantities that can be measured? One is clearly the scattering angle, right, because I have fixed the coordinate frame in my lab already, right. So, clearly I can measure that. What else? I can measure the energy of the final state, correct. Energy of the initial state is fixed by me, okay, but I can measure the energy of the final state. So, these are the raw measurable quantities, okay, but in practice it is more useful to turn these around, okay, and construct two other quantities. I am just going to take the scattering angle and energy, that is really what I measure, but just some change of variables, okay, and you will see why these change of variables are more useful than just the angle and the energy, okay. So, what are these change of variables? I am going to write them down, okay. E1, E2, when I say E1, E2 they refer to the electron energies, okay, not the proton. 1 minus cos theta, okay. So, remember these two are the ones that you measure. So, I just rewritten it, and the xb is a q squared over 2 the dot product, a 4 momentum dot product actually of the proton 4 momentum dot q, okay, which again is E1 E2 1 minus cos theta, that is just in the numerator, the 2 goes away, and then I have MP E1 minus E2, okay. If I go to the rest frame of the proton, this is what I get, right. So, again this you measure, this you measure, this you measure, and you got this quantity, okay. So, why go to the trouble of doing this? First of all, what is q square? That is just the momentum transfer squared, the thing that we have been seeing before, right. But what is this xb? This is one of the most important observables or variable in this business, deep inelastic scattering. Okay. It is called the Bjorken variable, named for James Bjorken, who unfortunately died very recently this year. It is also known as the Bjorken X basically. That is why I put the B. Not many people put that little b as a subscript. I like to put it to remember Bjorken. Okay. This is basically one of the most important things, in, if not the most important variable constructed specifically in the context of deep inelastic scattering. So, what does it mean? I am going to heuristically say that it is, okay, the fraction of the proton's momentum carried by the struck parton. Okay, what do you mean struck parton? So, in this picture an electron comes and strikes a parton inside, right. These three blobs are the partons, right. So, I am claiming that this xb basically, this entity measures what is the fraction of the momentum of the proton itself carried by one of these partons inside, the parton that you actually hit from with your electron. Okay. But if you think about it for 1 second, right, that statement makes no sense, right. Why? You can ask, for instance, what if the proton is at rest, right? Then what momentum of the proton are we talking about? Correct? Then how can you talk about a fraction of the momentum, right? And also, there is another question. Can't the partons, right, the 3 partons in this case, can't they fly off in random directions? So, partons fly in random directions. If that is the case, what right do I have to talk about the fraction of momentum carried by a parton? Correct? What if they are not parallel to the proton, right? So, what I said here is not the complete picture. This is just a very colloquial or very heuristic way of saying it. Okay. What we have to do is, this is a cunning due to Feynman. Okay. Basically, we have to go to what is known as the infinite momentum frame. So, the answer to these questions is, we are operating, okay, in the infinite momentum frame. Okay. What does that mean? Okay. So, this is also known as the bright frame. It means literally what it sounds like. Basically, you have to imagine seeing this proton from an inertial frame which has infinite momentum. So, basically the V of the frame that you are going to sit in, right, the V is basically very close to C, but not really, it is actually not even that, right, it is infinite momentum basically. Okay. So, it might be a bit crazy, but then we can always do some calculation there and come back to this frame, come back to our frame, the laboratory frame, right. After all, the laws of physics have to be the same in all frames, right, all inertial frames. So, let me draw a picture to convince you why this is a good idea. This is a frame where the proton now, okay, I want to draw in green. Okay, the proton now looks like this, right, there is some length contraction. So, actually spherical objects do not actually get length contracted when you actually view them. They still look like spheres. That is a result due to Roger Penrose. Let us neglect that. Okay, let us imagine there is a length contraction, and the proton carries. Okay, this is supposed to be starting. This arrow is supposed to start from the proton actually. So let me draw it again. This is the proton. The green is the proton, and the proton actually carries energy EP and momentum PP. Okay, and the proton has mass MP, of course. Now the parton I am going to draw with red. Okay, and the parton carries momentum XB EP XB PP. That is the 4 momentum. Okay, how was this possible? That is because in this frame, because you are viewing everything because you are in the infinite momentum frame, it is only the longitudinal momenta that actually matter here. Okay, that means in this frame you can neglect the transverse momenta. Okay, that is the whole point of this. Okay. Now that means all the motion is confined to only one direction, only the longitudinal direction, right. By transverse momenta I mean momenta in these directions, but now all your motion is confined to only the even a proton at rest in this frame will be moving with some energy and momentum, right, in the longitudinal direction seen from this frame, correct. So this is the frame in which we are going to operate, and I am going to wrap up this lecture by writing out the equation that shows this, and then in the next lecture we will make use of this Bjorken X, okay, and finish up deep inelastic scattering there. So now it is very simple to see what is going to happen, right, because what is now the partons invariant mass squared, that is just XB proton plus the momentum transferred squared, correct. Look at the Feynman diagram or look at this diagram for instance, right, that is what it has to be, right, from. So you take this vertex in the Feynman diagram, right. So the gamma comes in with momentum q, and this is P, this is basically P1, but then we are talking about the proton, the parton getting scattered now. So we have to take the momentum of the parton, which is x times P1, PP1, right, that is what I am writing here. So in the final state, if I want to get the 4 momentum of the final state, I have to add up the 4 momenta of these 2 initial states at that junction, right. So that is what I have done, and easily enough that means XB is nothing but q squared over 2 PP dot q. Okay, where q square is nothing but minus q squared, capital Q squared is nothing but minus small q squared. Okay, so when we write capital Q we want to keep that quantity positive, that is what it means. Okay, and this is what we saw before, this was the Bjorken X that we saw before right here. Alright, so I will stop here. In the next class we will take up more about this Bjorken X and put it into the quark parton model and understand how we get the structure of the proton from it. Okay, alright, I will stop here, see you in the next class, thank you.